any of these possibilities will generate an electric field. The simplest is looking at changing B. You change E, you get a B. If you change B, you would expect to get a electric field. Well, it turns out that you get an induced electromotive force or voltage just by varying the magnetic flux through a closed surface or through a closed conducting loop. It's that simple. And of course, this is basically an induced voltage or induced potential. So we call it an electromotive force, but I've always hated that word because it's not really a force, it's a potential difference. In other words, you're producing an electric field inside the wire to drive current. And of course, there's a couple different ways of expressing a potential difference, right? I'm going to express the fundamental way because it's useful conceptually. To calculate a voltage, how do you do it? You integrate an electric field over some region of space, right? So minus E would be related to this. Or I mean minus this potential difference would be related to this. Let me point that out because changing B begets E, if you will. Inverse to changing in E to get a B. That's all I'm sort of pointing out. So this thing looks very similar when you approach it this way. But more importantly, we can express this induced potential in terms of a induced current and based on the amount of resistance that's present. I'll put a little minus sign. That's induced, not induced. In other words, simplest case, vary a magnetic field. You generate an electrical potential which has an associated induced current. Of course, that current is regulated by the amount of resistance in the path. So that's essentially what we're going to look at today, and that's our experiment. So we'll spend more time on the actual discussion of information, but just to kind of lay this out, let's think about a simple case of this, just to make life. Let's give a calculation. That's basically trying to say. You like calculations, right? So let's assume that we have a surface area of, I don't know, say 0.05 meters squared, and we run it in a magnetic field. And I'm just going to have the magnetic field be at a perpendicular angle, or a parallel angle, if you will. B is parallel to A. Okay, so we don't have to deal with any weird angle business. And we have a magnetic field that varies with time. Say from 0 Tesla to 2 Tesla over 0.5 seconds. First of all, what is dB dt? Or I should say, even more directly, what does the expression of change in magnetic flux look like for this situation? By the way, for those of you that are late, I handed out basically sort of an overview on the relationship between all of these electromagnetic lines. So what do we have? The change in flux should be related to, well, B is constant over the surface area. I'm going to write this in two steps. We have B, if you will, dA. I'm going to write it this way. I'm going to take d dt of that. So first of all, A is independent of B. B is constant in terms of its orientation with respect to A. So B will vary, but it's not going to be integratable. It's going to be uniform throughout the surface A. So this reduces to dB dt dA. And we'll assume that the cosine of 0 degrees is 1, so we're not going to deal with any of that weird angular crud at this point. So we basically have this, or if you will, A dB dt. And this quantity should be equal then to minus this induced electromotive force, or induced voltage. So, first of all, what is dB dt? And if you will, deflux dt. Let's put some numbers with this. So we have 2 divided by 0.574.
Well, it seems like that's kind of more of an average change.
Assume it's linear. Assume it's linearly changing. Yes, I'd give you a function if it wasn't. But for now, so dB dt, if we assume the average, or the average dB dt, if you will, would just be 2 Tesla over 0.5 seconds, or 4 Tesla per second. And the flux, we've only got one coil, so again, it's just going to be B dt dB dt times A. And the A was 0.05, just to keep it simple, so what does that give us, 0.8? 0.08? 0.08, 0.8. Something like that. Did the math right? 4 times this. Oh, not 8, I'm sorry. 4 times that is going to be 2.2. I know, I screwed it up. It's okay. And this is dB, or dP.
Okay.
This is opposite. This is your electromotive force. Okay. Now, question is, why is this negative? Why might this be negative? Just conceptually, why might we expect this to be negative?
Because there's a higher electric potential inside as opposed to outside. You said that is.
This is the voltage in this loop now. So why would we expect it to have a negative value, if you will? Or why would the electromotive force be negative 0.2 volts? Right, because 0.2 Tesla meters squared per second is another way of saying a volt.
When you take the angle of EVR, you know, essentially infinitely far away minus close, and
It actually has nothing to do with that. It's not a charge, taking a point charge and moving it in closer. It's driving charge internally. So think about it this way. That little minus sign alone is what's referred to as Lenz's law. And one little minus sign. Right? The reason for it doing that is that in order to drive energy, or in order to drive current across, you got to use energy. Where does that energy come from? whatever it is that's producing the changing magnetic field. That could be somebody taking a magnet and doing this, right? Physical work. It could be changing the current in an electromagnet or in a coil, causing it to rise. But that would still require work. But what does the current do? What does the current, if the current's produced because of this electromotive force, what does it generate?
Are you looking for work?
No. It generates a magnetic field.
Oh, well, yeah, okay.
Well, if you've got a magnetic field and the current generates a magnetic field in the direction of the changing field already, what's going to happen to the field? It's going to perpetually change. It's going to change even more by the presence of the current being produced. In other words, by inserting energy, if the current produces a magnetic field in the same direction or in the direction of the change, then you're going to put more work, you're going to get more work, more energy than you actually put into the system. Does that make sense? It's like friction going in the direction of motion. So if you pushed on something and kinetic friction built up and that was pointing in the same direction of the push or the same direction of the movement, what would happen to the movement? It would actually increase. Well, where's that energy come from? Where would it come from? Okay, but what generates a magnetic force? The current, and what generates the current? Magnetic field. So the magnetic field and its change and the energy associated with that change is going to limit the amount of electrical energy you drive through this wire. Right? There's always a limitation in nature. We call it conservation of energy. So what it means in principle is when you generate current, it takes work. It doesn't produce work. So when you change the magnetic field, the current that's produced actually opposes the change in the magnetic field. It resists it. In other words, all the minus sign indicates is if you're increasing the field upward, the field generated by the current is going to be downward or opposite the change in the flux. It opposes d phi dt. In other words, if we have d phi dt as an upward increase this way, the induced magnetic field by the wire is going to oppose it, not add to it. So what the minus sign does is it tells us that the direction of the magnetic field is opposite the change in the flux that's produced by the current. So what direction of current? We have a potential difference. What would be the direction that the current would need to flow to produce a downward magnetic field inside this loop? It would have to go this way, right? So it would generate a current that flows this way, because that current will generate an opposing magnetic field to the increasing magnetic field in the opposite direction. It's an opposition effect. It's a drag effect, if you will. That's all the minus sign means. When you do the calculation, the minus sign means nothing in the calculation. It's a potential difference. Got 2 volts, 0.2 volts. But the direction of those 0.2 volts is the direction required to generate a current to oppose the change, not to add to it. Okay, so the effect is a drag effect. So that's the only thing this minus sign does, is it allows us to establish the direction based on how this is changing. Okay? We'll have to spend more time with that, but that's what the lab is based on, at least part of the lab. So ultimately then, if we wanted to calculate what the current is, if this is equal to I times R, and maybe we give R a value of, say, make it something other than 5 ohms, then the magnitude of the current would be 5 times 0.2, 1 ampere? No,
Two
yeah.
divided by 5.
divide by 5, excuse me. So 1.04. So the induced current would be 0.04. But the direction would be this way because the change in flux is upward, so it produces a downward current. Okay, so you got it, really, this is a note card. What direction is the change happening? It's going to oppose the change, right? It's contrarian, if you will. Whatever the direction of the momentum is, it always goes the opposite direction. So that's the idea of Faraday's law, and you're gonna have to spend time with that. I sort of threw it out there now because we've got 1 week to basically integrate all of this stuff together. So today's experiment is gonna basically be looking at both sides of this. But you're gonna have to spend some deep time with the calculators. Are pretty easy. But the deep time comes from figuring out orientations of right-hand rule and figuring out, well, if a flux is changing in a particular direction, it's increasing or decreasing, then the response will be opposite of that. It's like pushing on a spring, the spring pushes back in the opposite direction. So it's some stuff to think about. So let's go and take a break and get the lab set up. There's not a huge amount to really talk about with this lab because it's pretty conceptual. Mostly just get a sense of how these things fit together. And I'll hand back your exams.
You really do.
This is